At the end of the last section, we did an example where we were drawing balls from a box, red or white balls, and asking questions like, what's the probability of drawing a red ball on the second draw if we drew a white ball on the first draw, right? Or we even went beyond that. We said, just what's the probability of drawing a red ball on the second draw? Things along those lines, right? What's the probability of a later event given an earlier one? But what if I were to change that up a little bit? What if I were to say, what's the probability of drawing a white ball on the first draw, given that I drew a red ball on the second one? Right, so what's the probability of an earlier event occurring, given that the later one occurs? And that's much more complicated. And to answer that, in comes section 8.4, this is Bayes' formula. And I'm only really going to use Bayes' formula and talk about it in the context of probability trees, like we drew at the end of the last section. So here's Bayes' formula in a nutshell. It's the probability of A given B, but here I'm talking about the probability of an earlier event A given a later event B. And the way you compute this is you take the product of all your branch probabilities leading to B through A, so leading to B through event A, and then you scale it, you divide it by the sum of all branch products that lead to B. Admittedly, this formula right now doesn't seem to mean a whole lot. It's much more clear when I have a probability tree to work with. So let's just jump straight into an example, and I'll put this formula up again in an example. So here's a probability tree behind me. I start, and then one of three events happens, either U, V, or W. Again, no context here, just purely abstract. U, V, or W occurs. Probability of U occurring, 0.1, probability of V, 0.6, probability of W, 0.3. Notice, by the way, these probabilities add to 1, as they must, right? One of these three events has to occur. And if probability U occurs, well then we've got probability of C occurring is 0.4, probability of not C is 0.6. If V occurs, probability of C occurring is 0.5, probability of not C is 0.5, again notice these add to 1. Or if event W occurs, probability of C occurring is 0.2, probability of not C occurring is 0.8. So here's what we want to know. Here's the question. Find the probability of, say, W occurring given that C occurred. Alright, so all you know is that C occurred. The question is, what's the probability of W occurring? And obviously it's not just 0.3, because that's just purely the probability of W occurring. But in comes Bayes' formula, right? I want to know the probability of an earlier event given a later event. Alright, so Bayes' formula says that to compute this, we're going to take the product of all branch probabilities, again writing down the full formula, product of all branch probabilities, product of all branch probabilities leading to C through W, and then we're going to divide that by the sum of all branch products to C. Alright, what does this mean? So what do I have in the numerator? I've got the product of all branch probabilities leading to C through W. Well, okay, so I want to get to C, I want to go through W. There's only one way to do this, is this branch path right here. So yeah, the product of the branch probabilities leading to C through W is going to be 0.3 times 0.2. And so on top we've got 0.3 times 0.2. There's only one way to get to C through W, so it's just a product of 0.3 times 0.2. Divided by, now I want the sum of all branch products leading to C. So, well, how many ways can I get to C? Here's one of them, through W, right? So we've got 0.3 times 0.2. How many other branch products do I have leading to C? How else can I get to C? Well, I can go through V, right? I can do V and then on to C, so 0.6 times 0.5. and I want to add that because I'm taking the sum of all these branch products, so 0.6 times 0.5. Plus, last but not least, there's another way to get to C. So we have this path, now we have this path, right? So through U and then on to C, so that's 0.1 times 0.4. And now we just have to compute this ratio. This is Bayes' formula applied. 0.3 times 0.2, this is 0.06 divided by 0.3 times 0.2 is, again, that's 0.06 plus 0.3 plus 0.04. That's 0.06 over 0.4. You can plug this into a calculator if you want, but it's 0.15. So there's our answer. There's the probability of W occurring given that C occurred. Right, so it's not just this branch product. It's not just 0.3 times 0.2. That's the probability of W and C occurring. But if I want to know the probability of W occurring given that C occurred, I would sort of want to weight this probability. I'd want to weight this probability relative to all of the other ways that C could have occurred. So that's what we're doing here, right? We're taking the probability of W and C, but then we're weighting it relative to not all possible outcomes, but just the outcomes where C occurred, so we have to scale it. This is what Bayes' formula does for us. And it's a pretty simple formula to apply, right? It's just what we did. It's take the product of the branch probabilities leading to C through W, which is what we're interested in, and then scaled by the sum of all of the other ways to get to C. We'll just do one more example. So here's a fairly difficult example. It's the following. We have two boxes. The first box contains a number of balls. The second box contains a number of different colored balls. Box 1 contains 7 red balls and 3 white balls. And box 2 contains 4 red balls and 5 white balls. So here's the experiment. A ball is drawn from the first box and then placed in the second box. And then a ball is randomly drawn from the second box. So here's the question. If the ball drawn from box 2 is red, what is the probability that the ball drawn from the first box was also red? So a fairly complicated question, and notice again here that it's asking about the probability of an earlier event occurring given a later one, right? What's the probability that we drew a red ball the first time around given that a red ball was drawn on the second draw? So we're asking about the probability of an earlier event given a later one. So this is a candidate for Bayes' formula. We've only talked about Bayes' formula in the context of a probability tree, so we're going to have to build a probability tree here. And notice that this really is a fairly complicated question. I mean, obviously they're not independent events because we draw the ball from the first box and then we put it in the second one. And depending on which color ball we draw the first time, that changes the probability of the colors of the balls that we draw on the second draw from the second box, because we're changing the number of balls. So in any case, let's build a probability tree. So I've got my start, and I either draw a red ball or I draw a white ball. What's the probability of these happening? There's 10 balls total, 7 are red, so probability of drawing a red ball is 7 over 10. Probability of drawing a white ball, there's 3 white balls, so 3 over 10. And then we perform our second draw. So we'll call this red 2 and white 2, and red 2 and white 2. Now we're really going to have to think about this. Alright, so the second draw. What do we have in the second box? We've got 4 red and 5 white. Okay? But if I drew a red ball the first time, I put that in box 2, And now what do I have? In box 2 now I have 5 red balls and 5 white balls. Right, so if I drew a red ball the first time, now I'm drawing this from the second box, and I have 5 red and 5 white, so the probability of drawing a red here is going to be 5 out of 10, and a white 5 out of 10. Similarly, if I drew a white ball on the first draw, I put that in the second box, and now in box 2 I have 4 red balls and 6 white balls. So the probability of drawing a red here is going to be 4 out of 10 balls. Probability of drawing a white ball will be 6 out of 10. Alright, and we're asked to find what's the probability of event R1 occurring, a red on the first draw, given that we drew a red on the second draw. This is what we're asked to compute. And now it's just Bayes' formula applied. Right, so I'm going to look at the branch product leading to R2 through R1. So it's actually this one. Leading to R2 through R1, so this path. And the branch product here is just 7 over 10 times 5 over 10. You can go with decimals here if you want. You could write that as 0.7 and 0.5, but I'll go 7 over 10 and 5 over 10. Divided by the sum of all the different paths, the probabilities of all the different paths that lead to this later event R2. So we still have this first one. We've got 7 over 10 times 5 over 10. Plus, there's another way to get to R2, plus 3 over 10 times 4 over 10. So this is 35 over 100 over 35 over 100 plus 12 over 100 is 47 over 100. Flip the bottom, multiply it, you get 35 over 47. Right, so again, we're asking about the probability of this branch actually occurring, right? The probability of drawing a red ball, given on the first draw, given that a red ball was drawn on the second draw. But to find that probability, we don't want just the probability of this total path occurring, this path of branches here. We need to weight that, right? So it's not just this value. We need to weight it relative to all the ways that we could draw a red ball on the second draw. So it's divided by its scale, or by the sum of all possible ways to draw a red ball on the second draw. And with that, I won't do too many examples of Bayes' formula. It's sort of the same thing every time. Once you have your tree built, if you're given a word problem where you don't have a tree built, we'll build your probability tree and then apply it. If you want to see more examples, there's several more in the textbook, but we'll stop here.